Good morning. This is November the 6th. This is Math 1314. Hope everybody's ready to have a great week. A couple of announcements. First of all, Exam 2 grades will be posted later today or tomorrow morning. When I post those, I will post those to your WebAssign gradebook. I did send an email to everybody in class today about how to get there, but if you go to your WebAssign homepage and you click on grades and then raw scores, and then exams, you will be able to see all of your exam grades, the exam 1 and the exam 2 grades. Like I said, I should post those later today or tomorrow morning. If you want a copy of the graded exam sent back to you by email as an attachment, you must request that by email. Just send me an email, and I will be happy to send you back a graded exam 2. All right. WebAssign homework. You have WebAssign homework that's due on Wednesday, November the 8th, sections 3, 4, and 3.7. Please get that done. Don't get behind on your WebAssign homework here this last month of the semester. Online office hours this week. I'll be available online Monday, Tuesday, and Wednesday in the evenings. Notice that my Tuesday hours in particular are a little bit different. I won't be online until 8:30 tomorrow night. But then regular hours on Monday and Wednesday evenings, 8 to 9. And then Thursday I'll also be online from 11 to noon. So please don't hesitate to come by if you have questions on something, whether it's WebAssign or some of the material that we're covering in class. Today, we are going to start talking about logarithms and also some basics about logarithms and then graphs of logarithm functions. Also, let me mention your exponential function homework. There was not really any homework that I assigned out of the textbook on that. Instead, I gave you an assignment that I'm not going to pick up for a grade, but I wanted to kind of present that assignment to you one more time. So I've given you some problems. I sent this out. I've posted this on my Google site, so you have some access to it. It's also in the notes from the last lecture as well. I want you to be able to graph exponential functions by plotting points. So plotting points means making a t-table, and I've actually provided the t-table for you and some suitable x values that I'd want you to substitute in. Remember, the most important thing with graphs of exponential functions is to try to decide whether the graph represents a growth curve or a decay curve, because those are the two basic shapes for exponential functions. We also talked about compound interest, and so I've given you a couple of compound interest problems. One where the interest is compounded quarterly, so it's compounded a finite number of times a year. And I've given you the compound interest formula when you have interest compounded like that, so like quarterly or semi-annually or monthly or something like that. Remember, I'm not going to require that you have this formula from memory. If you have a problem that requires this formula in your next exam, I will supply the formula to you. You could also have interest compounded continuously. And continuous compound interest has a different formula that involves the number e. It's a equals pe to the rt. Once again, I will not require that you have that formula for memory. So a little bit with compound interest. And then finally, graphing functions, and in particular graphing exponential functions, and in particular f of x equals e to the x is the graph that I want you to know something about. And so let me go ahead and sketch that one in here. Remember that e to the x goes through the point 0, 1, and it also goes through 1e. Don't forget that e is approximately equal to 2.718. Right? That's a decimal approximation for e to 3 decimal places. E is actually, remember, just like pi is a decimal that does not terminate, does not repeat. It's an irrational number. So e to the x goes through 0, 1, and then when x is 1, y would be e. So you get the 0.1e, which is about 2.7. And you have this growth curve. Right? And so that is the graph for the function e to the x. I definitely want you to know that graph. All right, and then what I have done is given you a couple of transformations of e to the x. Don't forget that there's a horizontal asymptote for e to the x. The horizontal asymptote is on the x-axis, and so it's at y equals 0. So you've got this horizontal asymptote. You can kind of see how I'm putting a little dashed line there on the x-axis on your graph. When the e to the x is shifted up or down, that horizontal asymptote shifts up or down. And so you need to sketch in that asymptote whenever you do a vertical shift of e to the x. If it's a shift up or down, then that graph is, or that horizontal asymptote is going to get shifted also. So make sure you sketch that in. All right, so on the graphs, I've given you a couple of graphs to look at. F of x equals e to the x plus 2. I'm not going to sketch these here at this point. I just want to talk about these graphs. This one is a shift up 2. And so this is one where the horizontal asymptote does get moved. So you need to sketch the horizontal asymptote also, because it's going to move up as well. The next graph is a shift to the left because of that x plus 3. This is a shift left 3. And so the horizontal asymptote does not get shifted on this one. And so the horizontal asymptote is still going to be sitting on the x-axis. And then 3 more graphs to finish out the exercise set. This is the number 8 is a shift to the right 2 because of the x minus 2. So that does not shift the horizontal asymptote, but then you have a shift down 3, and so that is a vertical shift, and so this horizontal asymptote gets shifted down 3 also. So sketch the horizontal asymptote again on this problem, because it's going to be moved, and it's important that you get that in there in order to sketch the correct graph. Number 9, you have a negative sign in front of the function, and when that happens, you're just changing the sign of the y value. So remember, that's a reflection, and this is around the x-axis. And then finally, when you have a negative sign in front of the x, here you're reflecting around the y-axis. So it's a reflection kind of left and right rather than up and down. All right, so remember these last 5 graphs all relate back to the graph of e to the x, and there's the graph of e to the x right there. And so that's definitely what I want you to be able to deal with. All right, so now we are going to go on to start to talk about logarithms and what logarithms are, what they mean, kind of go from there. So logarithms is our topic of the day. So this is a big deal. It's an important application. And it's also something that a lot of people aren't real familiar with, and so it's important to kind of, this is an important lecture because I know for a lot of you who are watching this video who are in my class, you have not dealt with logarithms before, and so this is really a new topic, and in some ways kind of mysterious with that name and everything. So please kind of go over this, this video very carefully. Work through problems out of the textbook. That's going to be very important, and do a lot of practice problems on this basic stuff with logarithms. All right, so our first objective, what are logs? What are logarithms? Right, that's what we want to talk about. And to get at this, what we're going to do is we're going to look at a compound. We're going to actually look at 2 compound interest problems. 2 compound interest problems. All right, so let's look at the first problem is, and we want to look at, we're going to look at continuous compound interest. And to look at, remember with continuous compound interest, we're using this formula, A equals P times E raised to the RT power. All right, and so our first problem is, let's say that we invest, or our principal is $10,000, and the interest rate, remember this is continuous compound interest, is, let's say, 5%, which is totally unrealistic. You don't get an interest rate of 5% these days, certainly. And let's say that the time is 10 years. So what we're interested in is, how much money do you have after 10 years? All right, that's the question. How much money, and that would be the A in our problem, or in the formula. How much money do we have after 10 years? That's really the question. All right, so this is a matter of substituting into the formula, and then it's a calculator question at the end. You'd have A equals 10,000 times E raised to the RT power, so R would be 0.05 and T would be 10. All right, so you'd get A equals 10,000 E to the 0.5 power, and then that would be where you could bring in your calculator. You'd evaluate E to the 0.5. Remember that E to the 0.5, the keystrokes for that are on a TI-82, the keystrokes, and I said TI-82, I don't know, TI-83 or 84 is what I meant to say. The keystrokes for E to the 0.5 would be to hit the second key first, and then hit the ln key on your calculator. And when you do that, that brings up that notation right there, and then enter 0.5, close the parentheses. And so E to the 0.5 power is about 1.6487. About 1.6487. I got this off of my calculator. And so we'd have A equals 10,000 times 1.6487. And so you get $16,487. About. Right, this is just rounded. 21 cents. That would be an approximation there at the end. And so that's how much money we would have after 10 years. All right. So remember, I talked about two compound interest problems. So I'm going to work another problem right alongside this one. And so on this one, let's say that P is 10,000 again. But in this case, we know A, we know the finishing amount is $20,000. Interest rate is still 5%. And T is our unknown. So the question in a problem like this is, how long before our initial $10,000 investment is worth $20,000. How long does it take before it doubles? Now, I do want you to notice the difference in these two questions. A really big difference here. This is how much, right? What were we after in this problem? What was our unknown? Was A, was the amount at the end. On this new problem, the question is how long. So now we're interested in finding time. And when we substitute into our formula, we have 20,000 is placed in place of A, 10,000 is put in place of P, then E to the 0.05 times T. And so notice T is our unknown in the problem. Notice where T sits is in the exponent of this expression, this exponential expression. All right, so this is really different as far as how we would solve this. Now, the first thing we might do to solve for T is we might divide both sides of the equation by 10,000. That makes sense to do that. So when we do that, we get 2 equals E to 0.05 T power. And so the question here is, when we get to this point, is how do we solve for t when it is in the exponent? This is really different as far as how we do that. How do you solve for that t value, that unknown, when that unknown is actually in the exponent of an exponential expression? Because if we're going to solve for t, we need to get that t by itself, and we don't want it to be in the exponent anymore. So how are we going to go about doing that? That is the central question here. And so the answer is not going to make you very happy when I write this down, because it's still unclear as to what I'm talking about. Definitely unclear what I'm talking about. But the answer is we're going to use logarithms to do this. This is where logarithms come into play in an expression, or at least one place where they come into play is to try to solve an equation like this, where the unknown, the variable, is in the exponent of an exponential expression like this. It's a really different problem than the first compound interest problem I did. So let's look at a simpler problem like this one, and we will return to this problem eventually. But how do we solve for the variable if it's in the exponent? So we're going to look at a simpler problem at this point. Look at a simpler problem, but one where there is a variable in the exponent. And the simpler problem is going to be 2 to the x equals 5. 2 to the x equals 5. Now, if you think about it for a second, this equation, right? Notice there's a variable in the exponent, but this involves the exponential function 2 to the x. And if I graph, and we've graphed this function last week in our lecture the last time, if we graphed 2 to the x, this is an exponential function. It's a growth curve. It goes through 0, 1, 1, 2. I'm just substituting in x values. And then 2, 4. And 3, 8 up here, like this. And we get this exponential function, this growth curve right here. Right? And what we were doing, when we started graphing these kinds of functions, is we were plotting points to do this, right? So I substituted in 0 and got 1 for y. Substituted 1 in for x and I got 2. Substituted in 2 and I got 4. Substitute in 3 and I get 8. Well, notice in our problem, our equation, 2 to the x equals 5, what we really are doing here with y equals 2 to the x is we're putting in 5 for y. It's kind of a reverse question. Instead of starting with the x value and calculating y, what I'm doing is starting with y and trying to go back and find what x is. Now, on my graph, if you look at the graph, y equals 5 is right here. And so if you go back to the graph, notice, sure enough, that there should be some x value right here. But the question is, what is it? What is that x value? Where when I use that, I get 5 for y. Now, one thing I do know is that it's between 2 and 3. Notice that 2 is too small because 2 to the second power is 4. 2 to the third power is 8. It's too big. And so there must be some number between 2 and 3 where I could take 2 and raise it to that power, and I would get 5 for the answer. Right? And so what is this number? That's what we want to try to get to, is what is this number? And so what we do is we use a new notation here. When I write 2 to the x equals 5, where x is the power I raise 2 to get 5, like that. And we write this in this form, that this power, whatever it is going to be written like this. that x is logarithm base 2 of 5. It's logarithm base 2 of 5. And so the common way to read that is log base 2 of 5. Now notice that that base, the 2, is written as a subscript below the word log right there. It's not in line with the word log. It's literally written slightly below it as a subscript. And that base of the logarithm is the same as the base on the exponential expression, right? This is a base 2 logarithm right here. This is a base 2 log. And notice this is a base 2 exponential expression, and they're the same. What does that log base 2 of 5 represent? It represents, and remember what x is right here, it represents the power you raise 2 to get 5. So logarithm base 2 of 5 is equal to the power I raise 2 to get 5. Now I know it still doesn't tell us what the number is specifically, but this is going to steer us in the right direction to think about a logarithm this way. So that's what I want to explore first, and then kind of go from there. Now one thing I want you to see here is that I have this 2 to the x equals 5. And this expression right here, x equals logarithm base 2 of 5, notice I put a double-ended arrow between those two. I'm saying that they're really the same thing, and that this is called the exponential form of the expression, and this is called the log form of the expression. It is really very important that you be able to go back and forth between logarithm form and exponential form when you're working with exponential functions and with logarithm functions. That's got to be very natural to kind of go back and forth between those two things. All right, so if we kind of wrote a few more expressions like this, so if we had 3 to the y equals 10, 3 to the y equals 10, then that would be the exponential form, and its corresponding logarithm form would be y equals, notice the number off to the side there, that y is the exponent, just like the x was the exponent in the first one. And this is y equals logarithm base 3 of 10. And what does this represent? It represents the power you raise 3 to get 10. Right, it's the power, and notice the exponential form says that y is the power you raise 3 to get 10. So once again, I'm going to write that down. I'm going to write this down multiple times. So this is the power you raise 2 to get 5. This is the power you raise 3 to get 10. All right, let's see, let's keep on going like this then. So 19 to the x equals 100 right here. Then the logarithm, that's the exponential form. The logarithm form would be x equals logarithm base 19 of 100. Right, and so this would be the power you raise 19 to get 100. And what we're doing is we're starting with an exponential form, and then we are writing the corresponding logarithm form. All right, so let's kind of write that on the next page here, like we just were doing here. So we have this exponential expression. If we have b raised to the x power is equal to y, like this, b raised to the x power is equal to y, then that's the exponential form, and the corresponding logarithm form would be x equals logarithm base b of y, right? And that would represent the power, right? This is what logarithm base b of y would be, the power you raise b to get y. So now I'm in section 6.3 of your textbook. This is section 6.3. This is on page 497. And I'm going to work through some problems on this page that are just going through and asking you to kind of translate back and forth between exponential form and logarithm form. And then we're going to actually evaluate a few logarithms also. All right, so starting off with problem number 6, you have logarithm base 4 of q is equal to m. And so notice this is the logarithm form of the expression. This is the log form. And now we are asked to take that log form and write it in its corresponding exponential form. Now don't forget that the base on the logarithm and the base on the exponential expression are always the same. So the base on the logarithm here is 4. So the base on the exponential expression is 4. And then don't forget that the logarithm is always equal to the exponent. So you have a log, and you have the base is b, let's say, times something, but it's always going to be equal to the exponent. A logarithm really is an exponent. It's just another way of writing an exponent. And so a logarithm is always equal to the exponent. So in our problem, the exponent is going to be m. And you have 4 to the m is equal to q, like this. Right? So logarithm base 4 of q represents the power you raise 4 to get q. Right? So this is our corresponding exponential form right here. All right, problem number 8. You have logarithm base 16 of y is equal to x. So that is our log form right here. And we're trying to write this in the corresponding exponential form. And so the exponential form would be, well, first of all, the bases have got to be the same. So the base on the exponential expression is 16. And you have 16 to a power equals something. And remember that the power is what the logarithm is equal to. And so in our problem number 8, the logarithm is equal to x. And so this is 16 to the x is equal to y. That's our corresponding exponential form. Right, that you're looking at the power, that logarithm base 16 of y represents the power you'd raise 16 to get y. All right, problem number 10. You have logarithm base y of x is equal to negative 11. And so our exponential form, right, that's the log form right there. The corresponding exponential form, the base on the exponential expression would be y. And this is y to some power equals something. Remember, the exponent should be what the logarithm is equal to. And so in this problem, the logarithm is equal to negative 11. So this is y to the negative 11 is equal to x. Y to the negative 11 power is equal to x. That's our corresponding exponential form. All right, let's see. Let's look at one more like that. Let's look at problem number 12. Number 12, you have logarithm base y of 137 is equal to x. So that's our log form. The exponential form here then would be the base is y. This is raised to the x power equals 137. Y to the x equals 137 would be the exponential form. All right, now let's go back in the other direction again a little bit. So this is problem number 20. So problem number 20, we start with a exponential expression. So this is x to the negative 10/13 power equals y. So that now we're starting with an exponential form, and we want to write this in the corresponding logarithm form. So we're going in the opposite direction when we're converting here. Remember, the base on the exponential expression and the logarithm are always identical, and so this would be logarithm base x of y equals negative 10/13. So remember, the logarithm is always equal to the exponent. So this, we have a logarithm equals, and it's got to be the exponent. This is the log form over here. All right, so remember, those two expressions, x to the negative 10/13 equals y, and logarithm base x of y equals negative 10/13 are the exact same expression. All right, let's look at problem number 24. 24 is 10 raised to the a power is equal to b. So that would be our corresponding exponential form. And the log form that goes with this would be logarithm base 10, right? The logarithm and the exponential expression have the same base of b is equal to a, right? The logarithm is equal to the exponent here. Now this last logarithm right here that we just wrote down, logarithm base 10 of b is equal to a, that's an example of what we call a common logarithm, a base 10 log. So there's a couple of abbreviations we're going to use here. So a base 10 log is called a common log. And the abbreviation for that goes like this, that logarithm base 10 of x is really, I mean, not really, but we're just going to write it as log x. So in other words, with a common logarithm, that's a base 10 logarithm. Common log is the same thing as a base 10 log, and we typically do not write the base in this case. It's understood to be 10. So for example, if I have this log expression, log of, let's say, 50, right? That's understood to be a base 10 logarithm. And so this is really an abbreviation for logarithm base 10 of 50. Right? So if you were going to write this in terms of its exponential form, we might write it like this, that logarithm base 10 of 50 is equal to y. I just kind of say, okay, what's logarithm base 10 of 50 equal to, right? It's the power you raise 10 to get 50. And so the exponential form that goes with that would be 10 to the y equals 50. Right, 10 to the y equals 50. So those are the same expression. One's written in log form, one's written in exponential form. All right, if we had, let's say, 10 to the 3x plus 4 is equal to y. So that's an exponential form. So the log form for this, well, this would be log base 10. So what do? I don't write the base down. I just write log of 3x plus 4 is equal to, and it would be nice if I wrote it right? Yeah, that's actually backwards. Sorry about that. So this is going to be 10 to the y is equal to 3x plus 4. That's better. Remember, the logarithm is always equal to the exponent. And so that would be the short notation for 10 to the 3x plus 4 equals y. That would be the log form, or the log notation for that. And we'd be using the abbreviation for the common logarithm. So common logarithms are base 10 logarithms. And you write it without writing the base down, right? So a base 10 logarithm is called a common log, and it's just written as log x. The base is understood to be 10, and we typically don't write it down. Another abbreviation for logarithms that we use, another common abbreviation for logarithms, is for when we have a base of e. So for example, if we have e to the 2x plus 1 is equal to z, if that's our exponential expression, well, the log form for that would be logarithm base e of z is equal to 2x plus 1, like that. That would be the logarithm form for that. But we don't usually write logarithms base e written out that way. We have an abbreviation for that. First of all, logarithm base e is called a natural logarithm. So that's a natural log. And the abbreviation for that one is we don't even use the word log for that. We use the ln abbreviation for that, and we say ln x. And so a base e logarithm, let's see, a base e logarithm is called the natural logarithm, and its abbreviation is ln x. Right? It's understood to be logarithm base e. So in our problem, going back to our problem, the log base e of z equals 2x plus 1, log base e of z is equal to 2x plus 1, we would abbreviate that as ln z equals 2x plus 1. And that would be our abbreviation. Okay, so we had e to the 5th power is equal to w. E to the 5th power equals w. That would be our exponential form. Then our corresponding logarithm form would be, since the base is e, this would be a natural log, and be the natural log of w is equal to 5. That would be the corresponding log form. Right? The base on the logarithm is e. When you write ln, it's understood to be base e logarithm. We just don't usually write it that way. You can, by the way. There's nothing wrong with writing it that way, but that's the abbreviation that we're looking at right there. The ln w equals 5 is the same thing as log base e of w equals 5. All right, and if you go backwards, if you have, let's say we have the natural log of 52 equals c, that's our logarithm. Natural log of 52 is equal to c. Then the exponential form for that, well, since it's ln, the base on the logarithm is e, and so the base on the exponential expression is e. Remember, the logarithm is always equal to the exponent, so the natural log of 52 is equal to c, means that c is the exponent. And so you have e to the c is equal to 52, would be the corresponding exponential form. All right, so to kind of recap that part, if you have a base 10 log, that is the common log. And instead of writing log base 10 of x, we write just log x. And a base e logarithm is called the natural log. And instead of writing log base e of x, we write ln x in its place. Right? They mean the same thing. All right, those are, I think I should highlight those two statements right there. It kind of writes all that out again, kind of in a concise form right there. So not a bad thing to kind of keep in mind right there. Also, let's not forget, probably a good idea to write this down also, that if you have y equals log base b of x, right, that's the log form, and its corresponding exponential form is b to the y equals x, right? That's the corresponding exponential form right there. So a good thing to kind of write that down. And then finally, let's write down this, that logarithm base b of x represents the power you raise b to get x. And let's kind of explore that a little bit more right now. So this is kind of summarizing everything we've just talked about with logarithms and exponential functions and their connection. All right, so let's look at some examples now like this. So let's explore that idea about what a logarithm represents. So logarithm base 5 of 25 then would be, what is this? This is the power, let's just say this in words, or let's write it out in exponential form first. So maybe that would be the thing to do. So if we said that that's equal to y, and let's just let's start with log base 5 of 25, and let's say that that's equal to something like y, then the exponential form would be 5 to the y equals 25. And that's actually something we can solve, right? That because we're looking for the power you raise 5 to get 25. What does y got to be? It's got to be 2. And so in this case, what do we have? That logarithm base 5 of 25 is equal to 2. The corresponding exponential form is 5 to the seconds equal to 25. Okay, we had logarithm base 3 of 27. So what would this be? This would be the power you raise 3 to get 27, right? That's what you'd be looking at here. If you wanted to, you could write this as logarithm base 3 of 27 equals y, the kind of the complete log form there. And then write it out as exponential form would be 3 to the y equals 27. This is the power you raise 3 to get 27. And again, this is one that we can solve. This has got to be equal to 3. Right? We know that 3 to the third power is equal to 27. Right now, I'm just writing ones down that we can actually evaluate by looking at them. All right? If you had logarithm base 4 of 1 over 16. Okay, well that one's, maybe you might have a little bit harder time with that, possibly. So let's write this out. Logarithm base 4 of 1 over 16 is equal to y. That would be the complete logarithm form. The exponential form that goes with that would be 4 to the y is equal to 1 over 16. And so what's got to be true here? The power that you raise 4, you got to get a fraction there, so that power has got to be negative. It's the only way that that would work. And so y would have to be negative 2 here. 4 to the negative 2 is equal to 1 over 16. That's the only way to turn that into a fraction like this. And so this is equal to negative 2. And this is because 4 to the negative 2 is equal to 1 over 16. Right, that's the corresponding exponential form. All right, let's say we have a logarithm base 9 of 1. Logarithm base 9 of 1. So if you're not sure what that is, you could rewrite this. That logarithm base 9 of 1 is equal to y. And so this would tell you that 9 to the y has got to be equal to 1. And so what power do you raise something so you get 1 as the answer? Well, that would be 0. 9 to the 0 is equal to 1. And so logarithm base 9 of 1 is equal to 0. And the reason why is because 9 to the 0 is equal to 1. That's the power you raise 9 to get 1. Notice this is going to be true no matter what the base is. You have logarithm base b of 1 is always going to be equal to 0. That's actually kind of a property that we can write out here, that logarithm base anything of 1 is equal to 0. So in particular, with the common logarithm and the natural logarithm, we can write that the log of 1, just because that would be base 10, remember, that's equal to 0, and the natural log of 1 is equal to 0, right? Those would be particular cases of that. So whenever you take the log of 1, whatever the base is, you're always going to get 0 as the answer. All right? So let's go ahead and write out a few other statements here. Let's say we have, this is problem number 44 in your textbook, 44. You have logarithm base 2 of 1/8 and then plus 4. Now the plus 4 has nothing to do with the logarithm here, so that just trails along. And so really what we're after is what is logarithm base 2 of 1/8. And like we saw before, if you said that that was equal to y, then you would know that 2 to the y has got to be equal to 1/8. And so y has got to be equal to, first of all, the 2 has to be flipped. And so that means the exponent's got to be negative. And so this would be -3. And so going back to our problem, logarithm base 2 of 1/8 is equal to -3. And then just the plus 4 just trails along, and then you just get 1 right there. All right. If you have, let's see, this is problem 46. You have log of 10,000. Now don't forget what log means. That's logarithm base 10. So this is logarithm base, and if you want to write it that way, that's fine. Do that. That helps you keep it straight. And so this is the power you raise 10 to get 10,000. Right? That's what you're being asked to write out right here. So you're saying 10 to what power is equal to 10,000. And because there's 5 zeros there, what do you get? That's got to be 5, right? 10 to the 5th power is equal to, well, that's not right. I can do this, I promise. So you have 4 zeros there, right? And so this is going to be 4 right here. The 10 to the 4th power is equal to 10,000. That's better, like that. So log of 10,000 is equal to 4. Log of 100, since we're talking about powers of 10 here, log of 100 would be equal to 2. Because what would you have here? Remember, it's a base 10 logarithm, so you have 2 to the 2nd power is equal to 100. Logarithm of 10, the log of 10 would be equal to 1, because 10 to the 1 is equal to 10. Remember, these are all base 10 logarithms. And log of 1, finally, we've seen is equal to 0. Because the log, no matter what the base is, of 1 is always equal to 0, like that. So 10 to the 0 is equal to 1 there. All right. The natural log of e, first of all. Let's look at the natural log of e. So remember that would be the logarithm base e of e, if you want to write it that way, or at least think about it that way. So you could think that, even if you don't write it necessarily, that's logarithm base e of e. Remember, that's what ln represents. And so this would be the power you raise e to get e. And this would be equal to 1, right? You're saying e to what power is equal to e? And that would be e to the 1st power is equal to e. And so natural log of e is equal to 1. Natural log of e is equal to 1. Definitely something you should know about the natural log, that the natural log certainly of 1 is equal to 0, but that the natural log of e is always equal to 1, right? Because that's how the logarithm's defined. It's the power you raise e to get e. So e to the 1st power is equal to e. So the natural log of e is equal to 1. In fact, I sometimes will ask those questions on an exam. So typically these are on an exam. So quite likely on this next test, very likely on exam 3, So if you're watching this video, this is good to know. You want to star this because this is going to be something that's going to be on your test. Very likely on exam 3. These 3 questions. First of all, I'm going to ask you what E is equal to. Right? And then I'm going to ask you what the natural log of E is equal to. And then the natural log of 1, what the natural log of 1 is equal to. Right? Those are 3 things that I'll ask. And so what are the answers there? E is approximately equal to 2.718, right? So I'd be looking for a decimal approximation there. Natural log of E is equal to 1, and the natural log of 1 is equal to 0. Those are things that, for example, if you're a business calculus student and you're a business major, some of you who are taking college algebra this semester are business majors, and you have to go on and take business calculus. It's going to be important, very important in that class. All right. All right, let's see. So continuing on page 497. A couple more problems. It says solve for x by converting the log form to exponential form. So solve for x, convert log form to exponential form. So let's look at those problems for a second. So this is problem number 26. You have log base 3 of x is equal to 2. And they're asking you to solve for x here. So what do? You write this in exponential form. So in exponential form, this would be 3 to the second power is equal to x. And so what does that give you? Remember, you're solving for x here. That x has to be 9. That's easy enough. Problem 28, logarithm base 5 of x is equal to 2. All right, so this, in exponential form, this statement would be 5 to the second power is equal to x. And so that would get you x is 25. Problem number 32. You have logarithm base 18 of x is equal to 2. And so this would mean that in exponential form that 18 squared is equal to x. And so x would be equal to whatever 18 squared is. I think that's something like 564, something like that. I'm sorry, 564 is not even close. 324, I'm sorry. Yeah, I wasn't thinking. Clearly, I wasn't thinking there. Problem number 34. You have log of x is equal to 3. Solve for x here. So there's no base written right here. And so what does that mean? The base is understood to be 10. So this is 10 to the third is equal to x. So x is 1,000. Right, 10 to the third power. Let's see. This is problem number 35. Natural log of x is equal to 2. So natural log of x is equal to 2 in exponential form. That's a natural log, so the base is e. So this would be e to the second power is equal to x. Use a calculator and raise e to the second power. And you get about 7.389. So that's approximately 7.389. Like that. Okay, so we're doing good here. Let's see. The next problem I want to look at. This is number 36. You have logarithm of 100, log of 100 to the 8th power. All right, so this is the log of an exponential expression right here. Now, don't forget here that 100, first of all, is 10 to the second power. So remember, this is a logarithm base 10, so that's why I want to do this. I want to write this as logarithm of 10 to the second power, and that would be to the 8th power like that, right? because 100 is 10 to the second power. And so that would give you log of 10 to the, remember you multiply exponents in that case, so this would be log of 10 to the 16th power, like that. Let me use the brackets that I put in here, like this. So this is log of 10 to the 16th power. All right, so now this is a little bit easier to deal with, believe it or not, because this is logarithm base 10 of 10 to the 16th power. So think about this for a second. If you want to write it as with the base, that's fine. So this is saying 10 to what power is equal to 10 to the 16th power? And that would have to be 16, wouldn't it? And so, and that makes sense. What power do you raise 10 to get 10 to the 16th? So notice this tells us that what we have, this is always going to happen like this, that if you have log of 10 to some power like this, log of 10 to some power, that this is always going to be x. Now this is true for base 10 logarithms only, right? So common logs only, this property is true. Right, that the log of 10 to a power is just going to be equal to that power like that. So for example, log of 10 to the 4th power is going to be equal to 4. Log of 10 to the negative 3rd power is equal to negative 3. Log of the square root of 10 would be the log of 10 to the 1/2 power. That would be 1/2. Right? That's a nice property to know right there, that log of 10 to the x is always going to be equal to x. All right, if you kind of do that in a reverse direction, if you take 10 to the log of 4 power, for example. Now, what about that log of 4 right there? Well, let's just look at that off to the side here, kind of separately for a second. Log of 4 is log base 10 of 4. And what does this represent? This represents the power you would raise 10 to get 4, right? That you know that if logarithm base 10 of 4 is equal to y, then what do you know here? That 10 to the y is equal to 4. Right? Well, okay. Well, you've got, notice that y and log of 4 are the same thing. Y and log of 4 are the same thing. So our problem over here really becomes 10 to the y. But what do we just see? That 10 to the y was equal to 4. Actually, this is just kind of a restatement of the first property that I have kind of highlighted up there. And that is, it kind of goes like this, that if you have 10 raised to the log of x power, you get x there also. And those two statements together, that really what you're doing is you're applying the base 10 exponential expression and a base 10 logarithm to x, and they're canceling each other out. This is an example of what we call inverse cancellation. So what we're getting here is that, I'm going to put those properties right next to each other, that 10 to the log of x is equal to x, and log of 10 to the x is equal to x, like that. These are both examples of what we call inverse cancellation, which we've talked about before. And what this is implying here is, or not implying, this is proving here that, that y equals log x and y equals 10 to the x are inverses. That those functions are inverses of each other. So if f of x is 10 to the x, that exponential function, then f inverse x is log x. That's the common logarithm. Right? So this is inverse cancellation right here. First of all, these two properties We're saying if you have a base 10 logarithm and a base 10 exponential expression and you operate with them together, one after the other on x, it's like you're not doing anything at all. It's called inverse cancellation. And what that's telling you is that log x and 10 to the x are inverses of each other. This will certainly also be true for common logarithms. The exact same kind of statements. So that if you have e to the ln x, you're going to get x. So the natural log is a base e logarithm, and the exponential expression has a base of e. And these basically cancel each other out when you operate with those in sequence on an x value. And so you get inverse cancellation for for natural logs also. So this is also inverse cancellation. That the exponential expression e, if you take e and raise it to a power, and then you have the natural log, and you operate with those in sequence, it's like they're canceling each other out. And so what do you get here? That y equals ln x and y equals e to the x are inverses. Okay, and so that means that if f of x is e to the x, then f inverse x is equal to ln x, that they are inverses of each other. Definitely need to know these pairs of inverses, especially these two particular bases, base e and base 10, because those are by far and away the most common ones to encounter. So those are definitely things that you should be able to figure out. All right, so let's see. Let's continue on with this. So let's think about this idea of inverses a little bit and start getting some ideas of what you can do and can't do with logarithms as far as their domains and ranges for the functions. And that's kind of where we're going to finish the day out. So if we have f of x equals e to the x, let's think about that graph for a second. Right, e to the x, we know, because we started the day today with this, that e to the x goes through the points 0, 1, and 1e. And so you have this growth curve for e to the x. There's e to the x right there. Remember, it goes through 0, 1, and it goes through 1e. And so its inverse, f of x, or f inverse x, is going to be natural log of x. And so what do? We know that these graphs are reflections around the line y equals x. Here's the line y equals x right here. Right, we've talked about that with inverses. And so if we just kind of interchange the x and y values there, we get 1, 0, and e1 right about there. And you get this curve right here. And this is the graph for ln x right here. Notice that e to the x has a horizontal asymptote at y equals 0, and so the logarithm graph has a vertical asymptote at x equals 0. So notice that's definitely telling you that you can't take the log of a negative number, right? That you notice that you can't do that. That the domain here for the inverse function is from 0 to infinity, right? Look at the graph right there. Notice the graph never goes on the other side or the negative side of the y-axis there. And so you're only using positive x values. That makes sense because think about what the exponential functions restrictions are. If you have f of x equals b to the x, remember that that base has to be greater than 0. Also can't be equal to 1. But more importantly for us, that b's got to be greater than 0. And so notice no matter what you do with the exponential function b to the x, no matter what power you raise b to, since b is always positive, you always get a positive answer, right? So if f of x is 8 to the x, doesn't matter whether x is positive or negative, you always get a positive answer. So f of 1 is 8 to the 1, or 8. F of negative 1 is 8 to the negative 1, or 1/8, right? You always get positive answers. So the y values always must be positive here. Well, so what does that mean about the inverse function then? It means that the inverse function, that the x values must always be positive. And so what do you have for the natural log function? X has always got to be greater than 0. For the common log function, x has always got to be greater than 0, right? You cannot take the logs of negative numbers. That's probably the thing to take from this altogether. You cannot take logs of negative numbers, right? Those are not in the domain for these functions. Something probably to highlight right there. Now, I wrote this for the natural log and for the common log right here, but again, this is true no matter what base logarithm you've got. It's just that these are the most common ones to encounter. Right, and then that certainly fits in with the graph that we sketched at the top there for ln x, right? That ln x never went on the negative side of the y-axis. You're always taking the logs of positive numbers only. All right. All right, so if we have to kind of finish class out today, then if we have a function like this, f of x equals log of x minus 3, right? This is a base 10 logarithm. So if we wanted to look at the graph of this function, one thing we know is we can't take the log of a negative number. So we're taking the log of x minus 3 here. What do we see for the domain for this function? That x minus 3, what we're taking the log of, has got to be positive. It can't be negative or 0. And so you get that x has got to be greater than 3 is our domain. So the domain for this function is from 3, open parenthesis around the 3, to infinity. All right, that would be the domain for log of x minus 3. All right, if we had the natural log of 2x plus 3, then what would be true here? The domain for this function, you can't take the natural log of a negative number or 0. So 2x plus 3 has got to be greater than 0. So if 2x plus 3 is greater than 0, then 2x is greater than negative 3, or x is greater than negative 3 halves. And so the domain for this logarithm function would be parentheses negative 3 halves to infinity, like that. All right, let's see. Let's do one more like that. Just about finished with what I'm going to do today. We've covered a lot of material here. So you have the natural log of, let's say, 5 minus x. So for the domain for this logarithm function, right, that expression, the 5 minus x has got to be positive. It can't be 0 or negative. So what do? You set it greater than 0 and you solve this for x. Now notice on this one, when you solve for x, you multiply both sides by negative 1 and you have to reverse the order symbol. So you get x is less than 5. So the domain on this one, it kind of gets flipped over, and this goes from negative infinity to 5, like this. So it's from 5, and it's everything to the left of 5, which is not the most common domain to see. But all right, let's finish this by taking these functions and looking at their inverses. So these three right here would be good examples, and we could kind of finish with that. So if we have f of x equals log of x minus 3, find f inverse. right? And we can kind of piece this together now. So first of all, this is a base 10 logarithm, so its inverse is going to have to be a base 10 exponential expression. All you do here, you have y equals log of x minus 3, is kind of use what we've talked about before for finding inverses. You switch x and y. Remember, that's what inverses do. They switch x and y, and then you solve for y. All right, so to solve for y here, this is a log form, and we'd have to write it in exponential form. The base on the logarithm is understood to be 10. If you get confused and you need to write that, that's fine. Write log base 10, that's okay. And so that's the log form. Its corresponding exponential form would be 10 raised to the x equals y minus 3. And then to solve for y, just add 3, and you get 10 to the x plus 3 equals y, and that's our inverse function. The inverse function would be 10 to the x plus 3. Right, so these two functions, f of x equals log of x minus 3, and f inverse equals 10 to the x plus 3. Those are inverses of each other. Let's do the second function I have up there, the natural log of 2x plus 3, and we'll kind of finish with that problem. So f of x, so another example here, f of x equals natural log of 2x plus 3. Find f inverse. So remember, this is a base e natural log right here. So let's see, let's first write this as y equals natural log of 2x plus 3. And then we switch x and y, so this is x equals the natural log of 2y plus 3. And if it helps you, write this as log base e, because remember, that's what natural log is an abbreviation for. And so then write this in its corresponding exponential form, and the exponential form for this would be e to the x equals 2y plus 3. And then solve for y, finally. So subtract 3. And then finally divide by 2. So you have e to the x minus 3 all divided by 2 is equal to y. And that would be our inverse function. So f inverse here, x would be equal to e to the x minus 3 over 2. Right, so these two functions would be inverses of each other. Natural log of 2x plus 3 and e to the x minus 3 over 2. So notice when you have a natural log in a function, its inverse is always going to have an exponential function with a base of e in it. Just like on the previous problem, if you have a logarithm function, it's a base 10 logarithm, its inverse is going to have an exponential with a base of 10. All right, so for textbook homework, let's look at some textbook homework here to practice this. You need to kind of get these basics for logarithms down, so it's really important to do these basic problems. So this is section 6.3, page 497, problems 6 through 35 odd. Problems, I guess I should have gone ahead and signed those, 37 and 39. So this is actually 6 through 39 odd. That's better. And then 43, 47, 51, 53. All right, and then some things with the functions themselves that we started talking about. This is section 6.4, and some features of the graphs, like the domains and everything. So this is on page 513, and this is problem 7 through 15 odd. Like that. Those would be good ones to look at. All right, so please kind of get started on this homework. Try to work some problems out of the textbook. Come by my online office for help if you need it. I'll be happy to help you out. Have a great day. Take care and be safe. Thank you.